Imagine if the ground beneath your feet could breathe, expanding and contracting with each season, silently exerting forces powerful enough to crack foundations, buckle roads, and cause billions of dollars in damage worldwide. This isn't science fiction. This is the reality of expansive soils, one of the costliest yet underestimated geological hazards on our planet. Today we'll uncover the fascinating science behind these breathing soils and explore why they are considered more destructive than earthquakes, floods, and tornadoes combined. So what exactly are expansive soils? These are clay-rich soils that behave like terrestrial sponges. When they absorb water, they can swell dramatically, increasing in volume by 10% or more. During dry periods, they lose that water and shrink, often leaving behind networks of deep, wide cracks that can extend several meters into the ground. This cyclical swelling and shrinking creates what geologists call shrink-swell behavior, exerting immense and often uneven pressure on anything built upon them. The secret ingredient behind this remarkable behavior lies in a group of clay minerals known as smectites, with montmorillonite being the most notorious culprit. To understand how these soils work, we need to zoom in to the microscopic level. At a molecular scale, these clay minerals are composed of incredibly thin stacked plates. Imagine them like a deck of cards, but at the atomic level. The magic happens when water molecules encounter these clay particles. Water molecules are electrochemically attracted into the tiny spaces between these plates, literally forcing them apart and causing the entire soil mass to lift upwards. Here's where it gets fascinating. The type of cations present in the soil dramatically affects the swelling behavior. Sodium cations cause the highest swelling of smectite clays, while calcium ions have lower swelling properties. This is why sodium montmorillonite can be particularly problematic for engineering applications. When dry weather arrives, the water molecules leave these interlayer spaces and the clay plates collapse back onto each other, causing the ground to subside. This creates the characteristic polygonal crack patterns we see in dried expansive soils. Some cracks can be 15 to 20 centimeters wide and extend 2.5 to 4 meters deep. The swelling pressures generated by these soils are truly remarkable. Expansive clays can exert uplift pressures of up to 5,500 pounds per square foot, enough force to lift entire building foundations. To put this in perspective, that's equivalent to having several automobiles pressing upward on every square foot of your foundation. This isn't a localized geological coincidence. Expansive soils are a global phenomenon found on every continent except Antarctica. They are particularly common in arid and semi-arid regions with distinct wet and dry seasons, which provide the perfect conditions for the destructive cycle of wetting and drying. Let us now explore the global hotspots. In the United States, expansive soils stretch from the Gulf Coast of Texas and Louisiana through the Great Plains of Oklahoma, Kansas, and Colorado, and into parts of the Dakotas and California. Cities like Dallas, Houston, and Denver are built on notoriously volatile ground, making foundation problems a common homeowner headache. The American Society of Civil Engineers estimates that as many as 1 in 4 homes in the continental United States has some damage caused by expansive soils. Australia faces similar challenges with what locals call cracking clays. These soils cover vast areas of the eastern states, particularly Queensland and New South Wales, affecting both agricultural lands and growing urban centres. In fact, approximately 20% of Australia's surface soils can be classified as expansive clay. In India, the Deccan Plateau is covered by enormous deposits of expansive soil called black cotton soil or regur. These soils cover approximately 20% of India's total land area, predominantly in states like Gujarat, Maharashtra, Karnataka, Andhra Pradesh, Tamil Nadu, and Madhya Pradesh. While fertile for agriculture, they pose significant engineering challenges for the region's rapidly growing infrastructure. While hurricanes and floods make headlines with their immediate destruction, expansive soils work their damage quietly over seasons and years, making them what I call a slow motion disaster. As you can see these facts, the gradual destruction makes expansive soils the costliest natural hazard most people have never heard of. Here are several concrete examples that demonstrate the real-world effects of expansive soils. Feel free to pause the video and take a closer look. Since we cannot stop the ground from moving, sophisticated strategies have been developed to work with these dynamic soils rather than against them. Pier and beam foundations represent one of the most effective approaches. These systems anchor structures to stable soil or bedrock deep below the active zone of swelling and shrinking, typically 8 to 15 feet deep. This allows the ground to move without transferring stress to the building itself. While more expensive initially, they often prove cost-effective over the building's lifetime. Post-tensioned slab foundations have emerged as another popular solution. These reinforced concrete slabs use a grid of high-strength steel cables that are tensioned after the concrete cures. The tensioning creates compression in the concrete, making it rigid enough to float on top of moving soil like a raft. This flexibility allows the slab to resist the bending forces created by differential soil movement. Waffle slab systems utilize sacrificial plastic forms to create voids on the underside of foundation slabs. When expansive soil swells, it moves into these voids rather than pushing directly against the foundation. The field of expansive soil management continues to evolve with new technologies and materials. Nanotechnology applications are showing promise, with researchers exploring nano-silica and nano-clay additives to modify soil behavior. These materials can improve shear strength while reducing swelling potential at the molecular level. Advanced monitoring systems now use sensors to track soil moisture and movement in real time. This allows for predictive maintenance and early intervention before significant damage occurs. Geosynthetic reinforcement using geotextiles, geogrids, and geocells has proven effective in distributing loads more evenly and reducing differential settlement. Molecular dynamics research is providing new insights into the fundamental mechanisms of clay swelling. Scientists are now able to simulate the behavior of water molecules and clay particles at the atomic level, leading to more precise predictions of soil behavior and better targeted treatments. As our cities expand into increasingly challenging terrain, and as climate change potentially alters precipitation patterns, the importance of understanding expansive soils will only grow. The next time you see cracks in a sidewalk or notice a door that sticks after rain, remember, you might be witnessing the slow, inexorable power of the ground that breathes. Until next time, keep exploring the amazing science beneath our feet. Thanks for watching.